Afternoon. I'm assuming everyone can hear me, so let's talk about HTTP2 and asynchronous APIs. So as mentioned, I'm Davey Shafik. I am a developer. I have been for about 15 years. I am also an author. I'm an open source contributor, predominantly to PHP and PHP projects. And I'm the release manager for PHP 7.1. This is new. Did not realize that was a 3-year commitment when I signed up, but there we have it. And most importantly, I'm at dshafik on Twitter, and that's the best way to reach me. I do work at Akamai. Who knows Akamai? Show of hands real quick. Cool. You probably know us as a CDM. We do so much more than that. Check us out at developer.akamai.com. And whenever I speak, I always mention prompt, which is something that I started at a previous company to get people talking about mental health and technology, so mhprompt.org. Now, I just want to point out, I recolored these slides yesterday because of the projectors. So if I missed something color-wise, I apologize. Let's talk about H2. So it's HTTP2, not 2.0, or H2 as the cool kids say. We know it's real because it has a logo. So what is HTTP2? It's actually two different RFCs predominantly. RFC 7540, which is the HTTP2 spec itself, and 7541, which is HPAC, which is to do with header compression, which we'll look at later. It was created by the IETF HTTP Working Group, which is headed up by Akamai's Mark Nottingham, which is really cool. So for those of you who are maybe a little bit younger than I am, who don't know the history of HTTP, the first release, 0.9, came in 1991. And not much was done until 1996 when we kind of went back and revised it and had HTTP 1.0. 3 years later, we realized that we could do better and released HTTP 1.1. And then absolutely nothing happened until 2009. And Google said, this is like the state of HTTP is just not great. Let's create something new, and we're going to call it Speedy. And eventually, in 2015, that became the basis of HTTP 2. So browser support is generally very important when we talk about anything to do with the web. And I'm really happy to say that 60% of browsers currently in use on users' machines support HTTP 2. That includes Chrome, Chrome Mobile, Firefox, IE 11 if you're on Windows 10, or Microsoft Edge. It also includes Safari if you're on El Capitan or iOS 9, and Opera, but nobody uses it, so who cares? The biggest feature of HTTP2 is that it's binary instead of plain text. This gives us two really great things. One is that it's a much smaller protocol on the wire, and it's much more efficient to parse, so we need less resources to deal with that. It is fully multiplexed instead of ordered and blocking. I'll get into that in a little bit, but mostly that means you can use one connection for parallel requests, which we'll see why that's really, really important later. It uses header compression, which I mentioned earlier, HPAC. Further reduces overhead, and it has a really cool feature called server push. And for me, this is sort of the holy grail of HTTP2. This is where a lot of the excitement is for me. And effectively, what server push allows you to do is to proactively push assets to the browser in response to a given request. So for example, they may request a HTML page, and you as the provider of that go, well, I also know you're going to need style sheets and JavaScript and images, so rather than you having to request those, I'm just going to go ahead and push those down to you proactively. And what this does is it actually pushes into the browser's cache, and when the browser does go to make that request, it already has the resource locally. So what does HTTP2 mean for you as an application developer? For the most part, it's completely transparent. It's going to be handled by Nginx or Apache. Nginx does not yet support server push. I've talked to them. It's not currently on their roadmap, which I think is a shame. But Apache does, and there are some great sort of proxies. Caddy is one, and H2O is another. I prefer H2O. So if it's transparent and it's something you don't really have to care about, what is the point, right? Just turn it on, forget about it. The point is that HTTP 1 sucks. We as developers have come up with a lot of techniques to improve performance of HTTP 1. Things like minifying and concatenating JavaScript and CSS, inlining small bits of JavaScript and CSS is known as critical path, using image sprites, data URIs, domain sharding, like a whole bunch of tricks that we've come up with to make HTTP1 performant. And unfortunately, all of these things are hacks. Like, they're very, very clever hacks, and they do work. But they are, at the end of the day, hacks to get around the limitations of HTTP1. So if we go back to this idea of using one connection for parallel requests, and explore a little bit about what this means and why some of the things that we have been doing now start to look like anti-patterns and can actually be detrimental to performance moving forward. So a simple use case, uploading multiple images. So idea here is you have an HTML form in the browser, 3 or 4 or whatever file inputs, and the user has chosen to upload, say, 3 images. So we have a client and a server. Thank you for Font Awesome for my icons. We create a TCP connection, and we submit the form, and those images get uploaded, just one giant request. It gets sent to the server, and on the server side, we may decide that we want to go ahead and put those in some sort of back-end storage, so whether that's Amazon S3 or Akamai Net Storage or anything else. And so we go ahead and make requests to that back-end storage and store those things. This is obviously terribly inefficient, but it's also something that we've probably all done on our road to performant HTTP. So we start to look at concurrency. Right? Let's start to use the high bandwidth that we've got, certainly here in other parts of the world, and use things like AJAX to submit all of those images in separate requests concurrently. And on the back end, we can also use concurrency and do the same thing to our back end storage. As we receive those individual requests, we send them off to the back end. It's a good start. What about APIs? Obviously, this talk is about APIs as well. So I have a very simple API that I use for this example, which is fetching a blog post with comments. So here we have a client. Now this time we're talking about code, obviously not a browser and a server. We go ahead and create our TCP connection, and we do a GET request. Don't look at my horrible URLs. We get back some JSON back, and that might look something like this. So simple JSON object, type post, ID 1, title, tags, author, comments, right? Nothing exciting about this. We then need to get the comments, so we make a request to that comments URI. We get another JSON blob back. Now, in a perfect world where we have wonderfully semantic APIs that are good and proper, and we don't care about resource usage, we would actually return a collection like this of just, these are all of the sub-resources that belong in that collection. And then we have to go ahead and fetch all of those. So we now make multiple requests. This is a lot of work. So here's our comment. And as you notice, we now have a link to the author and all this extra sub information. So to get this data that we need, we're submitting 6, potentially 14 different requests if we want to get things like the comment author information, maybe their bio pictures, all these kind of things, right? It's a lot of requests and possibly connections depending on how you're doing this. We want to improve on this. So let's look at multiplexing. So multiplexing is this idea that we can create a single pipe through TCP, and we can send multiple requests through it concurrently. So we send off all of our requests, and we get all of our responses. So this is great. We've eliminated the overhead of all those separate TCP connections, and we're doing things concurrently with sort of no extra work on our part. All right, let's take a look at some code, because I think this is a little easier to understand on the code side. So these examples are in Python. If you don't do Python, I apologize. So we're going to start off with this. Number request is 378. Now that might seem like a random number to some of you, but what I'm going to be replicating is this little test here. So this is something you can see at http2.akamai.com. And essentially this is 2 different things that are going to happen in the browser. The first one on the left-hand side that you're seeing right now is it's loading 378 tiny little tiles over HTTP1 to create this image. As you can see, it takes almost 17 seconds. On the right-hand side now, we have HTTP2, which has multiplexing and concurrent requests, and you can see it's a lot faster, right? So we're going to replicate this test in Python. So here we have some Python code. We're going to use PyCurl. Now, the reason I'm using that is because, at least when I wrote this, requests, for example, did not support HTTP2, but curl is fantastic for H2. And we're going to do a simple for. So for I in range, num requests. go ahead and create the curl client, set some options. So in this case, it's the URL, and we tell it where to write the responses. Then we go ahead and execute that request. Okay. When we do that, it takes 20 seconds. So that is 378 requests in a simple for loop, 20 seconds. If we want to do this with HTTP2, it's very, very similar. All we have to do is add an additional option here, which sets the HTTP version to HTTP version 2. And when we do that, it now takes 34 seconds. This is not ideal, and we'll get into why that's the case later. But I put this up here because I want you to know that HTTP2 is not a magic bullet. There are certainly circumstances where using H2, because of the way that it works, because of backwards compatibility, is and can be slower. So let's now look at concurrent requests. So we're going to do this with HTTP1 first, and we're going to use what's known as curl multi. So we create a curl multi object. We go ahead and set pipelining to 1, which is to use HTTP1 pipelining. And then rather than execute the requests directly, we go ahead and append them to this handles object, and then we append them to the multi object, curl multi. And then we go ahead and execute them concurrently with this bit of code that I hate, and it's the same in every single language I have this code in. Effectively, we have 2 while loops. The first one will continue executing until we get our first response, and then from that point, the second while loop will pick it up and will actually handle those responses. And when we do this, we drop down to 6 seconds. So from 20 seconds to 6 seconds, and this is just HTTP1. This is a great improvement. Let's take a look at the same thing with HTTP2. Again, very small changes needed. We simply change pipelining to 2, and of course we add our version HTTP2 as well. Otherwise, no other changes to this code. And this horrible code is identical as well. And when we do that, we now go down to 4 seconds. So we started at 30-something, or 20 if you take H1. H2 of multiplexing, we're now down to 4 seconds. This is in the right direction. This is good. All right. I'm going to steal some of this. I don't think it's stealing water at this point, but. All right, so why did turning on HTTP2 initially slow us down? The reason for that is HTTP2 negotiation. So there are 2 different protocols sort of within HTTP2. There's H2, which is HTTP2 over plain text, and then there's H2C, H2 is HTTP2 over TLS, and H2C is HTTP2 over TCP, so plain text. With H2, we negotiate this upgrade from H1 to H2 through the ALPN negotiation for TLS. So it's just part of the TLS handshake. With H1, we actually submit a separate request and we ask for the upgrade. And what that looks like is here we have an upgrade H2C header. We also send some HTTP settings. And then on the response side, if we support HTTP2, we say 101 switching protocols. And at that point, that TCP connection becomes HTTP2. Now, you can actually send any type of request to initiate this, but you do have to wait for the full request body to be sent before you can start. So if concurrency is important to you, you're going to want to start with something like an options or a head. But effectively, this kind of negotiation has to happen also with TLS. And that's where we get the performance overhead in our initial example, because we are essentially creating 376 separate clients with separate connections, all doing this upgrade request. So anytime where you have essentially a single connection doing a single request, it's always going to be slower with HTTP2 unless we have something called prior knowledge, which allows us to skip this step. Now, all browsers require TLS for HTTP2. And this doesn't look like it's going to change, and I support this. We now have Let's Encrypt, so there's no excuses not to have a valid SSL certificate. And with this concept of multiplexing, where you can have one TCP connection, the overhead of negotiating TLS is effectively null and void. Now, as I mentioned, you can do direct connections with HTTP2 with prior knowledge. Essentially, this is entirely a performance enhancement. It assumes that both the client and the server both know they're doing HTTP2, and they send a simple connection prefix instead of this whole negotiation. All right, so server push. As I said, this is my favorite bit. So we saw multiplexing earlier. It's okay. Problem with this is that we're still making sub requests. We're still having to send all of those sub requests for the comments and the individual comments and all this kind of stuff. So what we do as developers, I don't expect you to read that. What we do as developers is we make a trade-off. We decide that rather than have all of these requests, which obviously add overhead, we are going to just munge all of these sub-documents into one larger document, and to hell with our wonderful API. So this is an example of said document. So rather than that very small post that we responded with earlier, we have the author information embedded right here. The comments now becomes an array with all of the comment information in there, and you'll notice they have the author information in them as well. This is even more ridiculous when I respond to my own post, so my author information is in there duplicated, and then someone else has commented again, so their author information is also duplicated. And yes, we can do sort of optimizations around this with sort of links within the document, but it's all kind of icky, and it makes our APIs not so great. So with server push, we can change this. So client, server, open up a TCP connection, do our GET request, get our response, okay? This is all the same. However, with server push on the server side now, what I can do is say, well, you've requested the blog post, and most people who do that, they want the comments, so here, have that. And here's the actual comments, right? Just go ahead and send that. You can also send all the author information, all the avatars. These are all discrete responses that when that client decides to make those requests, it already has cached. What's really cool about this is that the client has control over whether or not it accepts that information. So you can just send all of this stuff to the client, and the client can go, wait, I don't need the author information right now, so I'm just going to reject that request. Don't actually send the data over the wire. One cool use case I had for that was if you're on mobile, for example, and you're on a degraded network, you might decide that certain parts of your application are not necessary to display, so you can just reject those pushes and just not display that information. It's great. What this means, though, is that CSS and JavaScript minification is completely unnecessary. CSS compression, gzip compression, multiplexing, and server push mean that all of those things that we did around minification, inlining, they're no longer necessary. So, HTTP2 is composed of streams. Each request and response is in a stream. They have an ID. They're comprised of subcomponents called frames. And they may have both a weight and a dependency, which are really important, as we'll see when we start looking at some architectures. So here we see stream dependencies. We have stream A. Stream B is a dependency on stream A. What that means is that no resources will be dedicated to it until stream A is sent to the client. And stream C is dependent on stream B, and therefore it will not be sent until stream B gets sent. You also have this idea of weights. They're between 0 and 256. This is a relative amount of resources that should be dedicated to this particular resource when it comes to sending it over the wire. So stream A has a weight of 1, stream B has a weight of 2, so it gets 2 times the resources of stream A, whatever that means in the context. Stream C has a weight of 3, so it has 1.5 times the amount of resources of B, and 3 times the amount of A. This is all figured out by client and server. That should have been one slide back. So as mentioned, frames. All messages are composed of frames, and these are very small packets of information. They're uniform. They have like a 9-byte length prefixed header. They're super easy to parse. And what's really cool is that you can interleave these frames, and they're associated with any given stream. So you can send one frame from stream A, one frame from stream B, one frame from stream C, and go back around. And this interleaving is how we have this idea of multiplexing. This is how multiplexing works. So here's kind of an example. So before, we would send post with the path, post, content type, content length. These now go in a headers frame. And then we have our body of data, which is a simple JSON object. This now goes in a data frame. And these are separate, discrete bits that can happen at any point in time. Headers always come towards the beginning of the stream, but the rest of it pretty much can come in any order. So we've looked at headers, or talked about headers quite a bit. We have HPAC. So Speedy had this concept of compressing headers. Unfortunately, it had a security vulnerability, which is that When you compress information that has lots of duplicated type content in it, it's actually a lot easier to figure it out what it means once it's encrypted. So what HPAC does is it uses a table of known values as an index, essentially. So each item in that table can represent either just a header or a header and a value, and some other parts of the request become part of HPAC as well. And these are either statically encoded or use static Huffman encoding. So this is part of that table. There are 64 entries on the default table. And you can see here some interesting ones. So for example, 4 path slash or 5 path slash index.html. We also have HTTP statuses, schemes. We have accept car set down there with no value. This is really interesting. But what's really cool about this is you as a developer, you can actually append items to this table and only send them once. And then you just send the index the next time you want to send it. So for example, if you have a session cookie, you send the cookie once, and then you just refer to its location in the HPAC table. So this can very dramatically decrease the amount of data you have to send over the wire. So let's look at delivering a page. Here we have our browser, server, open up a connection, get index.html, get our response. And now with server push, we decide that we're going to start sending our critical path CSS and JavaScript. So instead of inlining them, we just go ahead and send them as a server push. Same for our logo, because that's quite important. We can then have a dependency on that CSS for font files or the rest of our JavaScript, maybe a splash image. And then finally, we could follow it up with the rest of our styles. And the way that this is going to work is that once the critical path is downloaded, the font will follow. Once the critical path JS is downloaded, the rest of your JavaScript will follow. By using dependencies and also using weights, we can deliver this in a very, very controlled way. And we be more performant with this browser not having to make requests to us. When we look at APIs now, we can do similar things. So client, I don't know why that is Chrome. Server, maybe it's Postman, right? Open up the TCP connection, send the request, get the response. And as I mentioned, we can do similar things. We can now start to push to our users. So in this case, we start sending the comments collection as well as the author of the post. We follow with a dependency all of the sub-resources for those comments. For the author, we send their bio image. And then we start following with the authors of the comments and so on and so forth. So, in summary, in brief, no more hacks. All of these things that we did to HTTP1, as I mentioned, some of them actually become anti-patterns. This idea of domain sharding, for example, we do it so that we can open more connections in current browsers. There's a limit of 6 right now, so we domain shard to make sure that we can saturate those big beefy pipes. In H2, where we have multiplexing, we only want to open one connection. So by domain sharding, we're now opening more connections than we need. That's more overhead than we need. As I mentioned, minification, compression, these things start to go away. Image sprites are no longer necessary. We just push everything down. That means all the maintenance around all that stuff is null and void. This is fantastic. It's going to simplify our workflows dramatically. There are huge performance wins, unless you do it wrong. It's a pretty obvious caveat, but there are certainly some huge performance wins here, and I think as we learn more about how we want to deliver things within this architecture, when we start to look at things like weights and dependencies, server push, and then we sort of tie that in with all the pre-browsing stuff like preload, prefetch, this can be pretty dramatic. 60% market share. This is out there. This is something we can use today. Server push, less so, but the rest of it is out there, multiplexing, it's all good. So in short, HTTP2 is awesome. Like, I'm really, really, really excited about HTTP2. Hope everyone here is as well. If you have any questions, I'm supposed to ask you to ask me outside. As I mentioned, at Shafik on Twitter, email if you want a response in several weeks. dshafik@akamai.com, and these slides will be available in white as opposed to black at daveyshafik.com/slides shortly. So, thank you very much.
Whew. Thanks, Davey.